Thanks for being here. I might say that if I was in your shoes, I would probably not be here. I would just be sleeping. So, yeah, I guess the good news is that it's hard for everybody. All right, so, in particular today, as I mentioned yesterday, I have a relatively fairly advanced lecture, so I need, your attention and my own attention, so let's see how it goes. I can already predict the answer. Anyways, so coming back to deep learning, right? So deep learning is basically everywhere, right? So in every device that you use these days, from voice recognition to playing games, you probably also the Go game, right, where the AlphaGo was able to beat the very famous champion, right, in Korea a couple of weeks ago, I guess months now. I showed you yesterday how we can use deep learning for doing navigation and all sorts of maneuvers with robots, right? And one of the applications where deep learning is really, really successful is, my favorite application ever, which is self-driving cars, right? And if we think of the, how the different AI communities or sub-communities are these days, everybody's really, really excited about, hey, numbers are going up, we're gonna maybe be able to solve, a lot of problems, right? And the question that we should be asking now is not, can we crank new numbers? What is the application we haven't tried? But what is next? Once we have, exhausted all these applications and all this, infinite number of papers with deep learning in the title. And so I'm going to quote one of my favorite researchers. And so what is the difference these days between computer vision and machine learning? Okay, and I let you decide whether it's true at the end of my talk, and you can decide whether I gave a computer vision talk or a machine learning talk. Okay, so here is Sonia and Seyen, right? So she's a faculty in Toronto as well. I guess she's around, not today, she's sleeping, but anyways. So computer vision, right, these days is all about, what can a neural net do for you? Okay, and probably this is going to translate to, again, medical imaging very, very soon if it's not yet there. And machine learning is actually, what can you do for a neural net? Okay, and I think this is actually quite, reflective of reality these days. If you go to NIPS, if you go to CVPR, what you actually see in the papers. Okay, so what is today's talk? So today I'm going to try to talk about different ways to introduce structure in deep learning, and in particular, I will spend most of the talk talking about the structure in the outputs. Okay, which is what I promised yesterday to whoever asked me the question. I'm not sure if he's still in the audience. And then if I have time, I'm going to talk about the structure in the loss function. And this will be related to the question of what if we want to directly optimize the metric, right? What if our loss function is non-differentiable? Can we still do something? And the answer is actually yes, and you will see it in, I guess, at the end of the talk. And if I have time, which probably I will not, I will show you how to also introduce a structure when you want to learn embeddings with deep learning. Okay? And this is very, very popular for text and images, but it might be actually something that you want to try in the medical domain. I haven't seen any papers that actually do that in that domain. All right, so let's start by the first topic, which is how can we incorporate the structure in the output? And why do we want to incorporate the structure in the first place, right? So if you think of the many problems that we have, let's say in computer vision or in medical imaging, we are interested in predicting more than just one random variable, right? And these random variables are actually statistically related. So if you think of some of the problems that I have here, right, if you want to do, let's say, tag prediction, and you want to predict whether somebody has a disease given, an MRI scan or something, right? So the different diseases are correlated, right? So when you do these predictions, you don't want to just do them independently, given the input, but you want to also try to look at the statistical relationship between, these output variables when you do prediction. Okay. If you do semantic segmentation, right? So we all know that two nearby pixels are typically very likely to have a similar label, right? There's one particular type of correlation that one should include. There is other problems where they're actually quite interesting. One of them is this problem I worked for many years, which is how to estimate the room layout of given a single picture. And it turns out that in that particular problem, we only have pairwise potentials if you formulate this with an MRF. So by definition, we actually need to incorporate the structure and the relationship between these variables if you want to do a good prediction. Okay, so I guess yesterday I talked to you about how to just do feed-forward nets. Okay, and so the way to look at these nets, right, is that we have a very complicated machinery to actually predict a function. Okay, and this function is going to be a function of the inputs. It's going to be a function of the weights that we're interested in learning, right? And it's going to be a function of the outputs, right? And you can think of it as when we predict in the last layer, we have as many outputs as the number of labels, right? So think about that as, where we index is a function of the output itself, right? But as I asked you yesterday the question, what was the graphical model of such a network, right? And I told you that is the same as having a single random variable, which is y, the output, right, which is multi-label. And what happens is that we are actually learning a very complicated potential function. Okay, and this is exactly what we are doing when we're training neural nets. And hopefully today this will become more clear to you. Okay, but if you look at how typically deep learning, how people train these networks, they're typically trained to predict one random variable. And so typically you do it by, let's say, minimizing cross-entropy, as I explained yesterday. So if your output has, you have multiple outputs, right? Let's say like the case of segmentation. So what do people do? So the way that people do is basically you try to predict every one of the pixels, right? The labels for every one of the pixels. And you basically have a loss function, which is a loss function of all the pixels, right? And it decomposes as the sum of loss functions over whether you get correct every one of these pixels, right? It's typically cross-entropy over the labeling that you have per pixel. And if you think about that, what you're doing there is equivalent to saying that I have as many examples as pixels, right? And just treating them independently. And it just turns out that they have overlapping fields, receptive fields, and this is why they're sort of correlated, but I never explicitly incorporate any correlations or anything in the output per se, okay? Is this clear? Yeah, hopefully. If this is not clear, man, let me know because we are going downhill from here. All right, so the question right of today is, can we do something better than that, right? So what people typically do is to say that we're going to train our nets to predict these pixel labels, right, independent for each one. And then what we're going to do is maybe smooth via an MRF. So this is a two-step process. And maybe some of you use Deep Lab. This is one great example of something of this form. All right, so the question for today is, how can we take into account the dependencies between the multiple variables, right, multiple outputs when we do prediction, and also when we train the network? Okay. Right, so you also the lecture, or a couple of lectures on graphical models, right? So graphical models are all about, can we look at the dependencies between the different variables, right? So maybe we can resort to graphical models in order to try to do that. So I'm just going to very briefly review what graphical models are in terms of the notation I'm going to use for this talk, okay, so that you're all with me. So traditionally, right, so everybody typically thinks of a graphical model as a grid with random variables which are at the pixel level, right? It's much more general than that. But it's a very convenient right, tool to express your dependencies between the variables, right? And you basically have to specify what are your outputs. In this case, I call every one of my random variables yi, right? And I'm going to encode an energy function which expresses what I think, which things are related, right? So I have typically unary potentials that only depend on a single variable. I have pairwise potentials that depend on sets of variables, of two variables, right? And I have high order potentials which depend on many, many variables, right? So a few years ago, it was very, very popular to have these high order terms. That has paid off for good or bad. So now so these graphical models, right, have been very, very useful in the past couple of years into solving a whole bunch or improving performance in a whole bunch of tasks, right? And one of the things that are very good at is in allowing us to incorporate our prior knowledge. Okay? And this prior knowledge can be incorporated two ways. One is in the way we parameterize the output, and the second one is in the way we actually define these potentials and in the way that we connect which variables are related. All right, so in computer vision, right, we typically make this distinction. It's whether the unary is pairwise, high order, all the stuff. For the purpose of this talk, and I think for the rest of your life, you should just forget about that. And just think about them as I have functions, and these functions depend on subsets of variables. Whether they're unaries, pairwise, whatever, doesn't matter, okay? The only thing that is going to matter is in how efficient your inference algorithm and your learning algorithm are going to be, okay? But there is no particular difference between these functions. Is this clear? Right, so yi here, when it's bold, it means that it's more than one random variable. So today I'm going to be talking about discrete Markov random fields. Okay, so think about every one of these yi's can have, let's say, k labels. Okay, let's say it's a semantic segmentation for every pixel, for example. Okay, and I have as many eyes as I have pixels in an image. All right, so this yr can be of any order, and what is important is that these functions have parameters. Okay, and I'm interested in learning these parameters. Okay, so when we talk about MRFs, right, sometimes we talk about their probabilistic interpretation, and so here I define just energy, which when you use them in practice is the simplest way is to just think about energies and forget about the partition function until you hit learning, okay. And then you can think of them as, I have a probabilistic model over all my random variables, and the only thing that I need to do is do the same trick as we did with the softmax. There's nothing else, right? So we exponentiate this energy, and we divide by the partition function. And this partition function is nothing but summing across all possibilities for my output. Now, in the case of yesterday, it was very simple because we only have k different possibilities, right? And then this partition function can be computed just analytically by just summing all the possibilities. Now, when we have, let's say, an image that we want to segment, right, and we have 1 million pixels, right, and for every pixel we have 10, let's say 10 or 20 possibilities, right, 20 to the 1 million is not something that we're going to be able to compute. And this is what is making graphical models complicated, right? And you probably already knew this after a custom lecture. Now, for the purpose of this talk, I'm going to talk about discriminative models. I let generative models for Max. Okay, so what means that we are interested in the conditional distribution of P of y given x. Okay, so x is the input, it's given to us, and given an x, we're interested in predicting the labels, okay, y. All right, so one thing to notice when you have these discriminative models is that you don't really care about P of x. Okay, everything is just conditioned on x, and that makes our life much easier. Now, inference in these graphical models is non-trivial typically, and so there is two types of inference that are interesting that you might encounter when you use them. One of them is map inference, where the idea is that you're interested in the maximum a posteriori, the configuration with the minimum energy is exactly the same thing. Okay, and so you typically have to solve a program of that form. Sometimes you're interested in making probabilistic inference, where you want to look at marginal distributions over a subset of variables. Okay? And depending on the learning algorithm that you're going to use, you're going to need to do either map inference or probabilistic inference. Okay? All right, so this typically either doing map or doing probabilistic inference is going to be NP hard. Okay? So it's going to be quite difficult to actually do any of these tasks. All right, so how do we do learning in these graphical models? So like everything in machine learning, right, we're given a set of examples. We have inputs and outputs. And as I mentioned before, we want to estimate these functions, right? The energy was a sum of functions over subsets of variables. And these functions can be sometimes shared, right, across potentials. For example, all pairwise potentials have the same type of functions. Maybe also the unary potentials have the same type of functions, right? So we want to estimate the weights of these functions. And like everything in machine learning, right, so what do we do is that we want to minimize some empirical loss. And again, we would like to use the test loss, but that's going to be difficult So again, we use this surrogate loss, and this can typically use hinge loss or log loss. Okay, so log loss is the same as cross-entropy, right? We saw that yesterday. Or hinge loss is this max margin, okay, coming from support vector machines, in this case, in the structure case. Okay, so this is the structure SVM for those of you that have heard that term before. Right, so we can just define whatever loss function we are interested in, and then we will try to do that minimization. Now, in graphical models, there is one assumption that everybody makes, which is the fact that these functions are linear in the parameters. Okay, so the functions depend on x and y. Okay, that's a table, right, in this discrete case, right, or a tensor, depending on how many y's you have, right. However, these functions, right, will always be linear in what you learn, and this is why these loss functions here typically are convex in the parameters. Okay, so that's good news that it's convex in the parameters, right. The bad news is that typically inference is NP-hard, so you can't really compute the optimal parameters typically. Okay, is that clear? Right. So these are very flexible in terms of trying to capture the correlations between the outputs. So that's good news. Bad news is that we assume that these things are linear, therefore they don't have a lot of representation power. Right. So it's up to you to hack up these functions phi here such that you actually can do a good job at prediction. So what do people typically do is that, as I mentioned before, they train a neural nets independently, right? That will give you maybe some unary potentials, some pairwise potentials, and then they learn in a second step a linear combination of weights. Okay? So what's the problem of that is that let's say these features, these deep features that you learn are actually not optimal for how you're actually making your prediction. All right, so if you think about them from neural net with a neural net hat, so what's happening is that these Markov random fields are very shallow. Okay, and they are very deep in the way that they look at the connections between the outputs, but they are very shallow in the functions that they use. Right, so how can we make MRFs less shallow, right, is by taking out this restriction that these functions should actually be linear, right? And if you take out these restrictions, so basically what you get is just you basically marry Markov random fields and deep learning. Okay, and this is what we call deep structure models. It's just a fancy name for something simple as well. Okay, so now with pictures, what I'm talking about is, right, in the lecture yesterday, we were predicting one random variable, yi, right, y1 here, and we have this box that was the CNN, right? So today we're going to have, this is not a graphical model, okay, so don't interpret it that way. So today we're going to have a whole bunch of nodes, and these nodes will be single variables, right, or sets of variables, and we're going to have CNNs or whatever you want, right, that is trying to predict subsets of these things. Okay, these are going to be functions that depend on either one random variable, two random variables at a time, and whatnot. Now, what are these links here that I put in red are the fact that when you have this BIST and you want to do inference, you have to be a little bit careful because it's not just doing a feed-forward pass, right? And the reason why is because this is predicting a variable and this is predicting two variables, but the variable here and this variable here are the same variable. So you have to somehow merge these predictions. And this is coming out of the math of the graphical models. Okay. But the intuition is that we're going to have a whole bunch of feed-forward nets that's going to allow us to compute potentials. Given the potentials, we have a particular Markov random field, and we can do inference. That's basically the idea. Okay? And please, if you have any questions as I talk, just let me know. All right. Okay, so how do we do learning in this case? So we can, again, compute a probability distribution, right, by playing the softmax trick. And remember that here, y is combinatorial, right? So this partition function here, we're not going to be able, in most cases, to actually compute it. So the way that we would do learning, right, would be by just maximizing the likelihood, right, which, as we saw the other day, I guess yesterday, is the same as doing cross-entropy, okay? Anyways, so forget about the math out there and just focus a little bit here. For how many of you have worked with graphical models before? I guess you guys are too young. You should absolutely look at graphical models. They're so beautiful. Anyways. All right, so for those of you that know the graphical models, so typically the way that we learn these graphical models, maybe you guys have seen RBMs, right? Restricted Boltzmann machines, which is just a particular type of MRF, right? So typically how we learn these models is by doing moment matching, right? So you basically try to compute the parameters of the model such that you match the moments of the data with the moments of the model. Okay, and what you see out here, once you look at the equations of cross-entropy, is that you are doing moment matching, but in the gradients. And so in that case, so why was I doing moment matching in the MRF is because I have functions that are linear in the parameters. Therefore, I actually get just the features here when I compute the gradients. Okay. Now I have a complicated, CNN for every one of these terms, right? So computing these derivatives is going to involve doing backward passes in all those different CNNs. All right, so, but we can use this expression, right? And so long as we can compute this probability distribution, so long as we can do probabilistic inference, I can compute the exact gradient. Okay. All right, so here is the first algorithm to actually learn these models. Okay. So how will it work? So we will compute the forward pass to compute the function which depends on all the random variables. Let's say, all my labels for the pixels. Once we have done forward pass to compute that, then we will compute the probability distribution by doing the huge softmax, right, over the combinatorial space. Then we will do a backward pass, right? Once we have P, right, we can just do backward pass as we saw yesterday. And once we do that, we can update the parameters by going in the direction of the minus gradient. Okay, so you look exactly the same algorithm as I put yesterday. Okay, so what's the problem? Now is when you guys should be awake. Any ideas? What's the problem? Can I do this in practice? I gave you a lot of hints as I was speaking. Maybe I was speaking too much. Nobody wants to guess? No? Free cocktail. Maybe free coffee is better today. No? Come on. Just guess.
I can tell you what Max said the week before.
He knows the answer, right? Yeah, Andrea. So.
Oh, he said Z.
Partition function, right? So there's actually two problems. One of is computing this. I told you before that it's typically NP hard. I need to compute this partition function, and that's a problem. The second problem is the way I brought it. This was the function that depends on all the combinatorics. I'm not going to ever be able to even store this in memory or anything, right? So this is a problem, right? So those are the two problems that I have, right? That my output space is typically too large, and I can't compute any of these two terms. Now, the first problem, this F, is very easy to solve, right? Because the way I actually brought this was by saying that it decomposes into functions that are functions of subsets of variables, right? So it turns out that I don't need to store this big guy, right, which is the full combinatorics. I only need to store these guys. Right? Is that clear? And these guys, I'm not going to define them in a way that that this is, all the random variables. Typically, this is unaries, pairwise, maybe three-way. That's it. Okay, so I can store that in memory. That's not a problem. Okay. So I can just, push the fact that this is just a summation over functions. So that's fine. And what do I do in order to address Max's comment, right? Is that, well, I can't do exact inference, right? I cannot compute the partition function, but I can do approximate inference, right? So Max was talking about doing variational inference. So that's something that I can do here as well. Max also mentioned that you can do sampling in his talk yesterday, right? So maybe I can do sampling in order to compute this thing, okay? So how will my algorithm look like now? So we'll look at the following, is that I'm going to do forward passes to compute this to compute these individual functions, not independent functions. And then I'm going to do approximate inference, right, to compute, let's say, the beliefs, my approximation for the probability distribution. And then I'm going to do the backward pass over all these different functions, and I'm going to update my gradients. Okay, is this clear? Right, so the only thing that I'm doing is now plugging in approximate inference. So if you look at this thing here, it's a double loop algorithm, right? Because I'm iterating, and then I have to call inference here. And inference is typically an iterative process. Okay, so inference in graphical models is hard, right? It's slow, it's nasty. So this, in general, is going to be a very slow process. Okay. All right, so what's the problem, right? We have to run inference in our graphical model, right, every time that we want to update the weights. We have millions of weights. Typically we do millions of these updates, right? So I have to run millions of times inference in graphical models. So that's going to be difficult in general, right? Okay, but let's look at what can we do in order to maybe overcome that issue, right? So first of all, right, we are again talking about big data, right? So we typically have a lot of training examples. So we can play the same tricks as we play with deep learning, right? We can parallelize across samples, right? So I can use any number of GPUs and then just aggregate the gradients from the different samples, right? And I can use mini batches, right? So I can do a stochastic gradient descent also to train these deep structure models. So that's good news. And so how can I handle the case that, for example, if I want to do semantic segmentation, right? I have a huge graphical model, and I need to do inference in this huge graphical model. Well, it turns out that a lot of these approximate algorithms that I use for inference can be formulated as a recurrent net. Okay, I can see the computations that, let's say, belief propagation or mean field do as a particular implementation of a recurrent net. Okay. So why is this a good idea? Because now I can use, let's say, TensorFlow, Torch, whatever, right, Piano, and I can do the computations in parallel and really, really fast. Okay, so that inner loop that does inference is not anymore slow, right? It's actually going to be quite fast. It's going to take, let's say, a few milliseconds. Maybe if I'm unlucky, 1 second or so. Okay, so now I will be able to actually do this double loop algorithm if I'm able to express my inference as a recurrent net. Is this clear? Okay. So a lot of these algorithms that people use, it's very, very simple to show that they are particular instances of recurrent nets. Why recurrent, right? Because I'm just doing an iterative process, and this iterative computation is exactly the particular operations that you will express as layers, let's say, in TensorFlow. Okay. All right. So how will this work, right? So now I'm going to do this parallel and whatnot. So what I'm going to do is I'm going to send different examples for different GPUs, right? I will fill the mini batch size for every one of these GPUs. Then every one of these GPUs is going to do the forward pass for the individual functions FR for the different examples that they fall into that GPU. Then once I do that, I'm going to do approximated inference, right, for every one of these examples by just running the recurrent net. Okay. And then once I do this, right, I can backpropagate through my gradients, right, to, I can backpropagate to estimate my gradients. It's difficult today. And I have a local estimate of the gradients for every one of these machines. And then what we do is something that I don't like, but is out there, which is to synchronize the operation that takes all the gradients from all the different GPUs. Okay, so we are looking now into how we can make this asynchronous. And then I can update my parameters. Okay, so now I have a fully parallelized algorithm. Everything is written as a neural net, and I can do these complicated deep structure models on GPUs. All right, so so there is something that in some cases is actually more efficient than doing that, because still doing belief propagation or doing mean field can be quite cumbersome if you have a very huge graphical model. Imagine your volume, right? And it's actually to try to get rid of this double loop algorithm. Okay, so
I guess last year we have a paper at CML that basically show how to do this. And so forget about the math. Even it's giving me a headache, so just don't look at the screen there. But the idea is that, so the way that learning can be phrased, right, is that you have to minimize this thing, right? And you can plug in an approximation of the log of the partition function that comes from just the way that people do LP relaxations for doing inference in Markov random fields, okay? And why is that important? Because you can write this partition function as a maximization problem. And then you can do duality, and you can end up with something that looks like, so forget about this, right, that looks like this, which is a minimization over two sets of variables, some additional set of variables. So you have the weights, right, that you're trying to train, as well as these lambdas, which are Lagrange multipliers coming from the dual. So these lambdas are the messages that you typically pass in message passing, okay? So why is this interesting? Because now you have written the problem of learning and inference as a joint problem, which is a joint minimization over the two sets of variables. And then you are free to do coordinate descent with whatever schedule that you want, right? Meaning that you don't need to run inference to convergence in order to do an update of the weights. You can update some messages, update some weights, do whatever you want, and you're more flexible. And basically, right, so you can do a little bit of inference, maybe just update a few messages, do some smart computation there, and then update your weights much more frequently. And I will show you in a second that actually that converges much faster. All right, so anyways, so then this is how the algorithm looks like, is that you do a forward pass to compute these functions again, then you update some of the messages, right, you don't need to do them all, you do backward pass, and then you update your parameters. Okay, and you can do this again in parallel by just distributing your examples across machines and whatnot. Okay. All right, so enough of the math. Okay, so if you were a little bit sleepy and you were bored by what I was talking about, so I'm going to show you some examples now. Okay, so it's time to maybe pay attention, and hopefully I can convince you that all the boring stuff that is not boring, at least for me, but maybe it's boring for you, that I talked before is actually worth looking at. Okay. All right, so as I mentioned before, right, so every time that you do neural nets, you have to show some kind of digits, some kind of characters or something. So here is my version of MNIST. So I guess this was my first year in Toronto, so yeah, so this is my approximation. I still was relatively sophisticated in the data. So what you see here is we created this very simple, this is a toy example, okay, I'm going to show you real examples afterwards. So we created this very simple example where we have words that are composed of 5 letters. These letters, we have these characters that have been, we have all sorts of distortions to them. There is also different backgrounds. And the idea is that you want to recognize all these characters, okay? So if you want to model this with a graphical model, how many nodes, how many random variables would you use? Remember, I tried to convince you yesterday that how you model your output was very important. So what would you do here? What's that? 15. Oh, so here I show you a couple of, so 50 you said. So the idea here is that we don't know how many words that exist in the vocabulary. So if we knew how many words that exist in the vocabulary, 50 would be, maybe a single random variable with 50 states would be a good idea. So what happens if we don't know how many words we have? So we can't do that a priori, right? So what do we do? How many letters do we have? 5, right? So maybe we can have a random variable. So great. So apparently the AC or the power didn't like this thing. So anyway, so we have 5 characters, right? So we can have a graphical model with 5 random variables, right? Where for every character we have a random variable, right? And the idea is that we want to predict the letters, right, for every one of these characters. Okay, so we created this kind of very simple synthetic data to sort of look at different aspects of this. Okay, so I have a lot of numbers here, so sorry about that. I'm going to just run you through these numbers, okay? So we have a graphical model, right, with 5 nodes. And so there is many things that we can play with. So we can play with what is connected to what, right? Whether we use connections with, we form a chain, or whether we connect things that are 2 characters away, right? So that's what you're going to be, when you're going to see here. So this is a first order model where it's basically just a chain where you can do exact inference. And this guy here, things are connected 2 characters away. So in that case, we have loops, right? So inference is hard in that case. What this thing says, we're going to use a fully connected multilayer perceptron. Okay, so very simple in terms of to compute the unary potentials. This means that we use a single 1-layer multilayer perceptron, and this means that we use 2-layer perceptron. Okay, and what you see over here is the results as we increase the number of hidden units. Okay, and so unary only means that we train to predict every letter independently. This will be what people do typically for segmentation. Joint training means that we train the model from scratch to take into account all the dependencies, right? Piecewise training will be what Deep Lab, for example, does, which is you train the unary and then you just train the linear combination. And pre-trained joint means that you start from piecewise training and then you continue optimizing this, okay? And what you see, the trend that you see out here in all these numbers, believe me, is that joint training helps, having more structures or more connections helps. The deeper that you have the neural nets, the better it is, and the more hidden units that you have, the better it gets as well. Okay, so all these different factors, right, that we were looking at complicating the model actually is for a reason. Okay, so let me show you some of the stuff that it learns. So here are the unary weights. So they're very, very simple filters. In this case, the pairwise potentials are just non-parametric. It's just a table. And these are the distance 1 edges, and distance 2 for the graphical model has links between variables that are 2 letters away. And what this is basically learning is the language model. Okay, so it's learning what correlates with what. All right, so we can also do, in this particular case, we can do the pairwise potentials to also be a multilayer perceptron, okay, and train the unaries, pairwise, everything together, right, with the MRF. And so this is the previous case where the pairwise were just linear, and these are just these different instantiations where the pairwise are also multilayer perceptron. And you see here that in general it helps to have nonlinearities also on the pairwise potentials. All right, so the next example is going to be a little bit more interesting. This is more of a real example. So in this case, we are interested in doing image tagging. Sorry, before I go here, any questions about this? Is it clear what we're doing? More or less? All right. So in this case, we want to do image tagging, right? So which means that for every image, we want to output a whole bunch of tags. There are 38 possible tags, and they co-occur together, right? So we have 2 to the 38 possibilities. It's binary, right? Whether that tag is good for the image or not. So what you see here, so our graphical model is fully connected, and it has 38 binary nodes. So this is if we use only unary potentials. Okay, so it's just, in this case, is AlexNet, I believe. Here, if we do this piecewise training, right, where we have non-parametric pairwise, and this is if we have joint training. Okay, so again, it's important to change the representation of, in this case, the convolutional network in order to take into account the fact that we have also these correlations to take into account that we use during prediction. And what you see here is what happens if we use this single loop versus double loop algorithm. Okay, so in blue is the the double loop algorithm that is much slower to converge, and in green you see the convergence of the single loop algorithm. Okay, so it matters quite a bit. You can actually speed up training. These are just some visual results of what the system predicts. Okay, so that's a fairly good job at predicting tags. So you can look at what are these correlations that it learns in the tags. right? So it learns things like, people and male co-occur together, but there are things like, let me see, like indoor and sky never co-occur together. So those are negative correlations. Okay? So it's basically learning into what goes together in terms of the context of the scene. Okay. All right, so here's another example of how you can do these deep structure models. So this case is semantic segmentation, and probably most of you have actually seen this or an instance of this before. So the idea here is that we're going to do semantic segmentation, let's say, on Pascal. So we have 20 classes, we have images of relatively big size, and you want to predict for every pixel the label, right? One of these 21 classes, so it's 20 classes plus background. So you have a fairly big graphical model in this case, so inference is hard. So in this particular case, we use a fully connected CRF with Gaussian potentials. So you can do very efficient mean fill doing these recurrent nets. So this algorithm that we publish at the same time as Phil Thor's group is very, very popular these days. It's called CRF as RNN. Unfortunately, although the two papers were put at the same time, they got all the fame for it, and nobody remembers that actually we have the same algorithm, shame on us. And the reason why is that they hack the system much better than us. So we have improvements that look relatively big, and then we stop working on it, and these guys hack it up to be 10% better. And that teach me a lesson is that force your postdoc to hack the numbers. I think that's better strategy. Anyways, so it's a very, very simple observation, but actually you can train this quite fast. All right, so you can also do things like instance level segmentation, which I think is something that is very useful in the medical domain, because you might want to segment cells, you want to segment certain tissues, right? And yes, semantic segmentation is not going to cut it, right? You want to get, for example, if you want to do counts of blood cells or something, you want to estimate every instance. So meaning that we, in this case, right, it's for autonomous driving, but as a matter, right, is we want to say that this is car, but also this is a different car than this car over here. Okay. So it turns out that you can do this. You can use a fully convolutional net to actually do this task. And the trick that we did is that the problem here is that the labeling is agnostic to permutations, right? I could have named this guy car number 1 and this car number 2, or it will be the same solution, right? If I call this car number 2 and this car number 1, and it's combinatorics on all these different cars that I have, right? So that makes learning a little bit more tricky. So one has to do matching and prepare an algorithm for learning. So instead of doing that, we were a little bit more lazy, and what we did is just break the symmetry by ordering that by depth order. And one of the reasons why we did this is I was interested in can we predict depth ordering at the same time. Right, so you can do this, and the difficulty when you do that is that your ordering will change. Let's say that if this car was not in the image, right, this will become instance 1, this will become instance 1, right, versus this guy, if this was not present, right? So it's not very good to, so it's difficult to generalize. So this is why we actually train the net in relatively large patches of up to 6 cars. Anyways, so that actually worked really well. And we have a Gaussian MRF that puts everything together. You can train this jointly. You can use recurrent nets again to train this as a deep net altogether. So this is ground truth on Kitty, and this is our results. So it segments actually pretty nicely, even the smaller cars. And what you see over here is 2 cars that, in this case, so this is a failure mode where they were together and at the same depth, so the net actually outputs that is the same car. We can do all sorts of other things. So this is something that I'm very excited about these days, which is mapping. And one thing that you can do is you can do these deep structure models to do mapping by, in this case, parsing aerial images and road images. So I wanted to show this here because if you look at aerial images and segmenting roads and whatnot, is very, very similar to what you guys do when you segment blood vessels. Okay, so maybe some of the stuff that we do here could be applied to that. So in this case, what we do is we can automatically segment high-definition maps and automatically realign the imagery from taken from the car as well as taken from the air. So we just released this data, which I convinced the German aerospace to fly a plane around Karlsruhe so that we have these aerial images of Kitty. For those of you that like self-driving cars, this is actually quite nice data. Okay, so here we can estimate things like where the road is, where the lanes are, where the parking spots are, where the sidewalks are, etc. And all this fully automatic. Great. So there's been. So I was talking today a little bit about a modern view of this, but there is actually many of the ideas that I talk about in these deep structure models go back to Léon Boutou and even before him. So in his 91 paper, the second part of the paper, which is very cryptic, is actually an instance of what I talk about today when you can do exact inference. Conditional neural fields are another example. Fields of experts actually have a lot of the ingredients here. And there is many other things that are related. And it's actually a very popular topic these days. How long do we have still? 15 minutes, okay. All right, so hopefully I will show you a couple of things in this 15 minutes, unless you guys have any questions now. No, okay. Right, so the next thing that we can do is try to incorporate this structure in the loss function. Okay, so I mentioned before that when we train these networks, we want to minimize the expected loss, right? And typically we do, this expectation is, we take the empirical expectation under the data, right? And so when we do supervised learning, right, the assumption is that we're going to do back propagation. Okay, so now I'm going to be talking about just neural nets. It doesn't need to be structured. It also applies for a structure, okay? But think about even in your very simple neural net, convolutional net, with a single random variable, that's fine. Right, so we require that we can compute the gradients, which means that the loss function has to be differentiable, right? And so many loss functions that, many of these metrics that we evaluated at test time are not differentiable, right? And this is a problem because we can't just put them as our loss function and then do back propagation through it, right? But for example, if you care about, let's say, detection, right, you care about average precision. If you care about segmentation, you care about intersection over union, right? And the question is, can we still train these deep nets to try to minimize this loss? That would be super, right? Because if we train using this loss, then we should be able to do well in that loss at test time, right? Assuming that we haven't overfit, right? If we train on cross-entropy, then at test time we will be good at cross-entropy, but maybe that's not so correlated with our loss function that we care about. Okay? So if you think of how we were so far training these networks, is that we said we're going to come up with a very simple surrogate loss, right? And this could be max margin, right? Or this could be cross-entropy. If you look at max margin, you can show that this is an upper bound on the task loss. Okay, so that's a nice fact, but this upper bound can be arbitrarily bad. Okay, and it turns out that in the presence of noise, this upper bound is really bad. So although it's related to the task loss, it's not so good. And cross-entropy, this is kind of interesting, right? Because we train the network with cross-entropy, and no matter how we evaluate the test time, we will always train the network the same way. So that seems wrong to me, right? Because if at test time I care about a very specific metric, right, I should sort of, let's say that in the medical domain, false positives or false negatives are more important, right? So I should take that into account when I'm training. Okay, and just reweighting things, is just a hack, right? So the question is, can I do something better? Can I directly minimize this task loss, even though it's non-differentiable and it might be actually structured, which makes things complicated? Okay, so I'm not going to bore you with mathematical details. I'm just going to show you the result. So it turns out that you can show that under some mild conditions, there is a particular update, which is this thing over here, which you can show that it minimizes computes the gradient of the expected loss function, of the task loss, for any loss function, even if it's non-differentiable and non-decomposable. Okay? So bottom line is that if you do these updates, okay, you are actually guaranteed to go in the right direction for your task loss, for this complicated loss function. Now, if we look at a little bit of how it looks like, so it's a expectation of the differences of two gradients, okay? And it's looking, for those of you that have worked with support vector machines or structured support vector machines, it's looking very similar to structured SVM, right? Do you see the difference? Maybe you have never seen extra. Who has seen structured SVMs in their life? Really? Who does ranking when they train the deep networks? No? All right, so you guys have a lot of things to catch up. So the difference, I guess, is that here we have two inference, to perform 2 times inference to actually do an update in the gradient, okay? So we do, this is the standard inference, and this is loss augmented inference. And in the loss augmented inference, we have actually positive and negative updates, okay? So it's a slightly different update rule, but it turns out that you can show that this slightly different update rule is going in the right direction, okay? All right, so this is actually an extension of a beautiful paper by McAllister that showed this in the linear case to the nonlinear case. All right, so bottom line is that it turns out that there is a very simple algorithm, right, which is basically you just need to do 2 times inference and compute backward pass, will allow you to train the nets to minimize what you want, okay? That's the bottom line. And in algorithm box, this is what the algorithm looks like. You do a forward pass to compute your function. You do these 2 inference steps. You compute the gradient. And then you basically, just by a single chain rule and by a single backward pass, and then you update in the direction of the gradient. Okay? Okay, so why should you care about this? So let me show you some examples, and maybe this will convince you that maybe it's actually a good algorithm. So this is not backpropagation, okay? It's a different algorithm that allows you to minimize these non-differentiable loss functions. So we try this in the context of object detection, okay, where you care about average precision. This is, in general for ranking. And so we started with some synthetic experiments, and what the bottleneck of the synthetic experiments was that if you know the network architecture is the same as what generated the data, then this thing kicks ass. Okay, it's really good. Why? Because then you are minimizing the true loss, you have the true model, and life is good. If you don't know the network architecture, then it's not such a clear winner, and the idea is that you have model error and you have at the same time loss error, and these 2 things, compensate each other. In the noise-free case, right, the model error typically dominates this loss error, and when you have noise, actually, this thing is much, much better. So why do you care about this? Because maybe in some of your domains, right, your labels are not noise-free, right? Maybe you have data that have label noise, right? And this is actually in the medical domain. I think this can be quite often the same as if you use internet photos or whatever with tags for us. Okay, so here is Pascal VOC, and what we did here is that we add label noise. Okay, so to simulate what would happen if you were more mechanical Turkey without so many validation steps. And you see as you flip labels that, so this is cross-entropy and hinge loss, right? And this is actually this algorithm, so it gets much, much better. It degrades much more gracefully with the label noise. So when you do object detection, so this was, sorry, for action classification, this is for object detection. So it's a little bit better when you don't add noise. And I think that Pascal is still a little bit noisy, perhaps. And that's why it's giving you a boost. But when you add label noise with 20% label noise, both cross-entropy and hinge loss just fail. And this stuff is still able to give us 20% AP. Okay, so it's still much more robust. All right, so should I finish here? No? 5 minutes? All right, so Sorry, guys. So in this 5 minutes, I will show you something that's actually quite, maybe quite interesting, maybe something different than what you have seen before. So these days you can, particularly people that do things on natural language processing, so NLP, right, text and images, they try to learn a common embedding that will be good for doing, let's say, generative captions or retrieving images or retrieving captions from images. So they try to embed images and text in some relatively low dimensional space. Okay, so we have seen some talks on manifold, but you can do the same thing also with deep learning. Okay, so people use this also for learning language models, so sentence embeddings, image embeddings, multimodal embeddings, etc. Have you guys seen any of this before? Yes, who has seen this before? Interesting. All right, so this can be learned in a supervised fashion or unsupervised fashion to, let's say, reconstruct the input, to predict context around, and Max will show a nice probabilistic way to learn maybe some of these embeddings, right, with, I guess, variational autoencoders. But sometimes we have access to extra prior knowledge that we would like to encode to learn better embeddings, okay? So we look at one particular type of prior knowledge that we have when we have text and images. And it's actually the fact that these text and images live in a visual semantic hierarchy, okay? So what do I mean by this? So let's look at this picture over here, right? So if you think of the word person, right, and the word woman, right, so woman is a person, right? So there is a relationship of entailment that happens. Or a woman is skiing is a woman and is a person, for example, right? So this is a hypernym relation, right? You can do this with sentences, right? I can say, I'm tired, or I feel that I have fatigue, right? Those two things entail each other, right? I can also say, if you look at a caption and an image, right? A caption is a more abstract way to describe the image. The image gives you much more information. Okay, so there is also this entailment relationship between images and captions. Is that clear? Right, so you can think of them as living in this hierarchy, in this DAG, actually. Right, so we wanted to create an embedding that satisfies this hierarchy relation. Okay? And you can think of this maybe using this to embed your data given hierarchies of illnesses, diagnosis, or something, okay? So it might be actually useful for the medical domain as well. So the way that we tried to encode this in the embedding was actually with a very, very simple idea, which is this notion of reverse product order. The idea was that we want to embed our representation of the input such that the more general concepts lie close to the origin, and you will have entailments if your coordinates are always bigger than, so there's entailment between two particular points if this guy here is to the bottom and to the right, meaning that the coordinates of this guy are always bigger than the coordinates of this guy, okay? And that's how we impose entailment. Is that clear? So the more abstract I get, the more close to the origin, the more precise I get, the farther away from the origin. And I can look at entailment just by looking at whether I am to the right or not. All right, so it turns out that it's too difficult to actually entail that, have a hard constraint, but we can use a very simple soft constraint to impose that, okay? And so there's a very simple loss function that you can use. So here is a very simple toy example. Okay, so we have this little hierarchical representation, and when we embed it, right, we have things like, so remember, now I flip it, okay? So now it will be to the top and to the right. So we have object is the most general thing, right? City, San Juan, right? So this is entailment ordering, right? A city, New York will be also another city. Okay, so there's again entailment, etc. Okay, is this clear? Right, so you have now all this relationship, and just by looking at 2 points in that embedding, you know whether they satisfy this relationship. So you can do this for image caption retrieval as well, and it turns out that you can do better image caption than the state of the art if you use this relationship. Why? Because men with cell phone happens a lot in Coco, right? And basically what you're saying is that all these images are just more specific representations of men with cell phone, let's say. Okay, and the last slide I'm going to show is that you can, so people show this algebra with these embeddings. You can do this interesting algebra that, for example, if you say you embed words and images at the same time, and you say I want the max between man and cat, and you retrieve the closest images, you will end up with images that have man and cat. Okay? Max of black dog and park, and this is what is, okay? If I do the max of apple and banana, I get images of apples and bananas. Okay? If I do the mean of these images, I will get images that have the only thing that is in common, which is horses and people. Okay? If I do the mean between this and dog, I will actually get images of dog. Okay, so you get this very interesting algebra operations. All right, anyway, so yeah, I talked already too much. So I show you all sorts of ways to incorporate the structure in the model. There is many other ways that you can do this, and there's a lot of stuff to be done in this domain. I just want to acknowledge the team behind the stuff that I showed you today, and thank you very much.